Dear students, in my last class, I have told you about the introduction to solids, and also in the solid 1 we have discussed about some of the points which we have not covered in the introduction to solids. So today let us take another one, that is solids 2. Here also we are going to learn some more aspects of the solids which we have not covered in the introduction to solids. Now here let us take the radius ratio. So in the introduction to solids also we have discussed about the radius ratio. Now what is this radius ratio? This is very important one to find out the coordination number of the solids and also the structure of the solids. In solids, the coordination number of an ion, that is the number of ions surrounding a particular ion, depends upon the radius ratio. In ionic solids, radius ratio is defined as the ratio of the radius of the cation to the radius of anion. Mathematically, it is given as radius ratio is equal to radius of cation, that is R plus, divided by radius of anion. Greater the radius ratio, greater is the coordination number of the ions. Let us take an example. In sodium chloride, sodium ion has coordination number 6. In cesium chloride, cesium ion has coordination number 8. This is because the size of cesium ion is greater than the size of sodium ion. Below I have given a table giving the radius ratio, range and corresponding coordination number and the arrangement or the structure of the unit cells. If the radius ratio is in between 1 to 0.732, then the coordination number is 8 and that unit cell is having cubic structure. If the coordination number is in between 0.732 to 0.414, then the coordination number will be 6 and the unit cell shows octahedral geometry. If the coordination number is between 0.414 to 0.225, then the coordination number will be 4 and the solid exhibit tetrahedral geometry. Lastly, if the radius ratio is in between 0.225 to 0.155, then the coordination number is 3 and the structure exhibit triangular geometry. Students, you must remember these radius ratios and also the coordination number and the structure to the unit cell. Based on this, let us solve some of the problems. The problems are most important one as far as the examination point of view. Let us take the first problem. The radius of the cation in a solid measures 33 picometer and the anion measures 70 picometer. Predict the coordination number of cation and structure of solid. In this problem, the radius of the cation is 30 picometer and radius of anion is 70 picometer. Therefore, radius ratio is equal to 30 divided by 70, which is equal to 0.471. This value lies in the range of 0.732 to 0.414. Hence, the coordination number of cation is 6 and the solid exhibit octahedral structure. Let us we take the another problem. A solid AB has the sodium chloride structure. If the radius of the cation A is 100 picometer, what is the radius of anion, that is B? Since the solid NaCl has octahedral structure where the coordination number of sodium ion and chloride ion is 6, the solid AB also possesses the same structure of sodium chloride with coordination number of A plus and B minus is 6. This is possible when the radius ratio is in the range 0.414 to 0.732. Now, thus the radius of cation divided by the radius of anion is equal to 0.414 to 0.732. Therefore, radius of anion is equal to radius of cation divided by radius ratio, that is 100 picometer divided by radius ratio 0.414 to 0.732. So this gives the range, that is the 241.6 to 133 picometer. Now coming to the another important aspect in solids, that is calculation of atoms in a unit cell for simple cubic, phase-centered cubic and body-centered cubic structures. To know about this, the following points are kept in mind while calculating the number of atoms in a unit cell. Each corner atom in a cube is shared between 8 unit cells. That means it contains in one plane the 4 unit cells and above contains 4 unit cells. Therefore, each corner atom is shared with 8 unit cells. Therefore, a corner atom contributes 1/8 to each unit cell. An atom on the face of unit cell is shared by the 2 unit cells, that is the side of the another cube. Thus, a face atom contributes half to each unit cell. An atom on the edge of a cube is shared by 4 unit cells. Hence, an edge atom contributes 1/4 to each unit cell. An atom inside a cube belongs to that cube only. Hence, that atom contributes fully to that unit cell. Keeping all these points in mind, let us calculate the number of atoms in a unit cell of a simple cube. In simple cube, an atom or ion or molecule are situated only at the corners of a cube. Each corner atom contributes 1/8 to a unit cell. Therefore, contribution of one corner atom is 1/8. Therefore, contribution of 8 corner atoms is equal to 1/8 into 8 is equal to 1. Hence, the number of atoms per unit cell in a simple cubic structure is 1. Similarly, let us find the number of atoms in a unit cell of face-centered cube. In a face-centered cube, there are 8 atoms at the 8 corners of the cube and 6 atoms at the center of 6 faces of the cube. Therefore, the contribution of one corner atom is equal to 1 by 8. Therefore, the contribution of 8 corner atoms is equal to 1 by 8 into 8 is equal to 1. Now, the contribution of one phase atom is equal to 1 by 2. Therefore, contribution of 6 phase atoms is equal to 1 by 2 into 6 is equal to 3. Hence, the total number of atoms in a unit cell of phase-centered cube is 1 plus 3 is equal to 4. Now, let us calculate the number of atoms in a unit cell of body-centered cube. In body-centered cube, there are 8 atoms at the 8 corners of the cube and 1 atom at the center of the cube. Hence, contribution of one corner atom is equal to 1 by 8. Therefore, contribution of 8 corner atoms is equal to 1 by 8 into 8 is equal to 1. Now, contribution of one central atom in BCC is equal to 1. Therefore, total number of atoms in a unit cell of BCC is 1 plus 1 is equal to 2. Hence, remember the simple cubic structure, the unit cell contains one atom. The body-centered cubic structure, the unit cell contains 2 atoms. And phase-centered cubic structure, the unit cell contains 4 atoms. Keeping these points in mind, let us take some of the problems based on this. Coming to the first problem, a compound XY crystallizes in the cubic structure. X atoms are situated at the corners and Y atoms are at the center of phases. What is the formula of the compound? Now, there are 8 atoms of X at 8 corners and 6 atoms of Y at the center of 6 faces of the cube. Therefore, contribution of one corner atom is equal to 1 by 8 and contribution of 8 corner atoms is equal to 1 by 8 into 8 is equal to 1. That is, the one X atom is present in the unit cell. Similarly, the contribution of one phase-centered atom is equal to half. Therefore, contribution of 6 phase-centered atoms is equal to 1 by 2 into 6 is equal to 3. So, there are 3 Y atoms are there in that unit cell. Hence, the formula of the compound is XY3. This is how the formula of the compound is solved. Coming to the another problem, a cubic solid is made up of 2 elements P and Q. Atoms Q are present at the corners of the cube and atoms P at the body center. What is the formula of the compound? What are the coordination numbers of P and Q? In this case, it is clearly given. Number of atoms of Q at the corners in unit cell is nothing but it is 1 by 8 into 8 is equal to 1. That means the Q atoms are 1 in the unit cell. Since it is a body centered, P is at the body centered in the unit cell, that is also 1. Therefore, the formula of the compound is PQ. Contribution of P and Q each is 8. Sorry, the coordination number of P and Q is 8. Now coming to the another very important aspect, to know the relationship between atomic radius, edge length and distance between the 2 atoms, that is D, in a crystal. Now, I have given this in the form of a table. If you take a simple cubic structure, the distance between the two atoms is known as d. Here the distance and also the edge length both are same. Hence d is equal to a. Coming to the atomic radius in simple cubic is r is equal to either it is a by 2 or it is d by 2. Coming to the body-centered cubic system, the distance between the two atoms d is equal to root 3 by 2 into a, that's equal to 0.866 into a. And the atomic radius is r is equal to root 3 by 2 into 2 into a, that's equal to 0.433 into a. Coming to the face-centered cubic structure, here the d is a upon root 3, that's equal to 0.707 into a, and radius is a upon 2 root 2, that's equal to 0.3535 into a. The relationship between atomic radius and distance between the two atoms d is r is equal to d upon 2. Now, I have given in case of the body-centered cubic, the distance, how we got that equation. So here I have shown. So apply the Pythagoras theorem for a square. There it is between the two edge length is a and a. Therefore, the diagonal it is x. Therefore, x square is equal to a square plus a square is equal to 2a square. Therefore, x is equal to a into root 2. Now, when we take, since in case of a body-centered cubic lattice, the atom is at the center. Now, the diagonal of that, so one side will be x, another side will be a, and the diagonal, at the center of that diagonal, the atom, the BCC atom situates. So, therefore, it is d and d. Therefore, I can say that 2d square is equal to x square plus a square. That results 4d square is equal to 2a square plus a square, that is equal to 3a square. So, therefore, d square is equal to 3 by 4 into a square. Therefore, d is equal to root 3 by 2 into a. In face-centered cubic structure, so according to the Pythagoras theorem also you apply here. So, the two sides are a and the atom is present at the center of that the system, the square. Therefore, 2d square is equal to a square plus a square, that's equal to 2a square. 4d square is equal to 2a square. Therefore, d square is equal to 1 by 2 into a square. Therefore, d is equal to 1 upon root 2 into a. So, this is how the above formulas you get it to the simple cubic, body-centered cubic and face-centered cubic lattice. Students, you must remember even these equations. Based on these equations, once again, you have to solve the problems. The problems will be asked based on these equations. Coming to the first problem. Cesium chloride has BCC arrangement and its unit cell edge length is 400 picometer. Calculate the inter-ionic distance in cesium chloride. BCC structure of cesium chloride is shown in the figure. half of the distance of CE represents the inter-ionic distance, that is D. According to the Pythagoras theorem, AE square is equal to A square plus A square, that is equal to 2A square. Therefore, AE is equal to root 2 into A. Now, let us take the CE. The CE square is equal to A square plus root 2 into A whole square. This becomes the 3A square. Therefore, CE is equal to root 3 into A. Now, the inter-ionic distance is nothing but CE upon 2. Therefore, here the CE upon 2 is nothing but root 3 into A divided by 2. The A is nothing but it is 400 picometer. Therefore, it is root 3 into 400 divided by 2, that gives 346.4 picometer. This is how you have to calculate and you have to solve the problems. Coming to the another problem, aluminium crystallizes in a phase-centered cubic structure. Atomic radius of the metal is 125 picometer. What is the length of the side of the unit cell of the metal? In this problem, the radius is given, that is 125 picometer, and here the asked is the edge length, that is A. We know that for phase-centered cubic structure, R is equal to A upon 2 into root 2. This is equal to 2 root 2 into R. This is for A, that is the edge length. This is equal to 2 into root 2 and radius is 125. That into 125. So that gives 353.55 picometer. Students, you go through such problems also from the textbooks and also the other books. Let us take the one more problem. Tungsten crystallizes in body-centered cubic unit cell. If the edge of the unit cell is 316.5 picometer, what is the radius of the tungsten atom? In this case, the given R edge length is given, that is 316.5 picometer, and here asked is the radius of the atom. We know that for BCC arrangement, the radius of the atom is equal to root 3 upon 4 into A. Since A is 316.5, therefore it is root 3 upon 4 into 316.5, that's equal to 137.04 picometer. Any solid having cubic close packed structure, it exhibit phase-centered cubic system. This is very important point which you have to remember. Sometimes they ask the solid is having CCP arrangement. CCP arrangement means it is having phase-centered cubic lattice. Now coming to the another important aspect, that is relation between density and edge length of a cube. Let the length of edge of the cube be a picometer, or we can also represent this as a into 10 raised to minus 10 centimeter. Now the volume of the cube will be a cube, a into a, that is length into breadth into height, that is a cube. Therefore, volume of the cube is equal to, if I substitute the value, it becomes a into 10 raised to minus 10 centimeter cube, which is nothing but a cube into 10 raised to minus 30 centimeter cube. Now coming to the density of the unit cell. What is density? It is mass upon volume. Therefore, it is mass of unit cell divided by volume of unit cell. Let us consider this equation as the equation number 1. We know that the mass of unit cell is equal to number of atoms in the unit cell, that is Z, into mass of each atom, that is small m. Let us we call this equation as equation number 2. We know that mass of each atom, that is small m, is nothing but it is equal to atomic mass divided by Avogadro number. Let us we call this equation as equation number 3. Substituting the value of m in the equation 2, I get the mass of unit cell is equal to Z into atomic mass divided by Avogadro number, that is 6.023 into 10 raised to 23. Let us we call this equation as equation number 4. Substituting the equation 4 in equation 1 and also the value of volume of a cube, we get density of unit cell D is equal to Z into atomic mass divided by 6.023 into 10 raised to 23 into a cube into 10 raised to minus 30 grams per centimeter cube, where Z is the number of atoms in the unit cell. For simple cubic structure, Z is equal to 1. For body-centered cubic structure, Z is equal to 2. And for face-centered cubic structure, Z is equal to 4. This is what you have to remember regarding the value of the Z. Based on this, let us we take some of the problems. Coming to the first problem. Copper crystallizes with face-centered cubic unit cell. If the radius of the copper atom is 127.8 picometer, calculate the density of copper metal. In this case, the given is atomic mass of copper is 63.505 AMU, Avogadro number 6.02 into 10 raised to 23 per mole, and also the radius of the copper atom, that is R is equal to 127.8 picometer. For FCC unit cell, the Z is equal to 4, and now A is equal to R upon 0.3535 for FCC system. Therefore, if I want to calculate the A is equal to R is the radius is given, that is 127.8 divided by 0.3535. This becomes 361.5. We know that the density of copper is equal to Z into atomic mass divided by 6.02 into 10 raised to 23 into a cube into 10 raised to minus 30. If I substitute the values for FCC, the Z is 4. 4 into atomic mass of copper is 63.55 divided by Avogadro's number, and the edge length, that is the 361.5 raised to 3, and substituting and simplifying this, we get 8.94 grams per centimeter cube. This is how you have to solve the problems regarding like this. Coming to the another problem, an element with atomic mass 60 AMU having FCC unit cell has a density of 6.23 grams per centimeter cube. Calculate the edge length of the unit cell. So what are the given things here? The given atomic mass is 60 AMU. For FCC, Z is equal to 4. Density is given, that is 6.23 grams per centimeter cube, and asked is the edge length, that is A. We know that the density is equal to Z into atomic mass divided by Avogadro's number into A cube into 10 raised to minus 30. Therefore, A cube is equal to Z into atomic mass divided by Avogadro's number into 10 raised to minus 30 into density. Substitute the values. For FCC, Z is 4, atomic mass is 60 divided by Avogadro number 6.02 into 10 raised to 23 into density 6.23. Here 10 raised to 23 and 10 raised to minus 30 becomes 10 raised to minus 7. And if I simplify this, I get A cube is equal to 63.99 into 10 raised to 6. Therefore, A is equal to 4 into 10 raised to 2 or 400 picometer. If I want to express this in terms of centimeter, this will be 400 into 10 raised to minus 10 centimeter. Or if I want to express this in terms of angstrom, it becomes 4 into 10 raised to minus 8 centimeter or 4 angstrom. Coming to the another problem, niobium crystallizes in body-centered cubic structure. If the density is 8.55 grams per centimeter cube, calculate atomic radius of niobium, and atomic mass of niobium is 93.4. Now coming to the given things, the atomic mass is 93 AMU, density is 8.55 grams per centimeter cube, and for BCC, Z is equal to 2. We know that the A cube is equal to Z into atomic mass divided by Avogadro's number into density into 10 raised to minus 7. So this value will be 2 into 93 divided by 6.023 into 8.55 into 10 raised to minus 7. So the value comes to be 36 into 10 raised to 6. So A will be 3.3019 into 10 raised to 2. That is nothing but 330.19 picometer. For BCC system, the radius, because here we have to calculate the radius. For BCC system, R is equal to 0.433 into A. So this is equal to 0.433 into 330.19. This becomes 143 picometer. This is how you have to calculate the radius. Coming to the another type of a problem called the packing efficiency. Calculate packing efficiency in cubic close packed structure. As I have said, the cubic close packed structure is in fact nothing but phase centered cubic structure. Here you have to calculate in a cube how much space is occupied by the atoms and how much space is empty. That is called packing efficiency. So for FCC, the edge length A is equal to 2 root 2 into radius, or radius is equal to A divided by 2 root 2, and the 4 atoms per unit cell in FCC system. That is the value of the Z. Now, the packing efficiency is given as it is equal to volume occupied by 4 spheres in unit cell divided by total volume of the unit cell, that is A cube into 100. It is in terms of percentage. This is equal to the volume occupied by the 4 spheres. So 4 into the volume of a sphere is given by the equation 4 by 3 pi r cube into 100 divided by total volume of the unit cell, that is A cube. You know the value of A is 2 root 2 into R, this raised to 3 for BCC system. For FCC system. If you simplify this, so I get 74.2%. It means in FCC, each unit cell is occupied by atoms with a volume of 74.2% and remaining volume is empty, called void volume. This is how the packing efficiency is calculated in the FCC system, or also cubic closed packed system. Similarly, you calculate the packing efficiency in body-centered cubic lattice as well as simple cubic lattice in the similar fashion. Students, today we have solved the many problems and also we have studied the two things. One is the radius ratio and another one is the number of atoms in the unit cell. Based upon that, you have calculated and also the density, packing fraction, all these atoms, all these things. Go through this once again and try to understand. Thank you.